And the next speaker is Boxin Shi from Peking University. The talk is entitled Data-Driven Photometric 3D Modeling for Complex Reflectances.
Okay, so thanks for the introduction, and thanks for Emily Sensei for inviting me here. It is my great honor and pleasure to give a talk on the Shitsukan Symposium. And my title today is Data-Driven Photometric 3D Modeling for Complex Reflectance. This is actually an inverse graphics problem. So the similar contents have been given at this year's ICIP tutorial and SIGGRAPH feature course. So this is a kind of a self-contained talk. So I start from introducing something about our photometric stereo basics. It not only covers the contents research from our own group, but it will cover some state-of-the-art progress about data-driven photometric modeling. So we are always interested in capturing the 3D information, like 3D imaging, by using a camera. This can be achieved by using laser scanner. This is a project done at the Ikabuchi Lab in University of Tokyo, where I got my PhD degree. And in computer vision field, this is also very popular to use a multi-view stereo so that you can get a rough gross geometry of an object. But it's difficult when there is textureless surfaces because the correspondence or the triangulation becomes difficult comparing to the laser scanned ground truth on the rightmost. And photometric 3D modeling is famous for its high accuracy. This is a project called 3D Scanning the President of the United States by Professor Paul Debevec from USC. And the setup was in the White House. So you can see actually President Obama's face has been illuminated from various varying lighting conditions and a very highly detailed geometry, as well as the surface reflectance can be reconstructed. Another example is the gel site. This is a microstructure 3D scanner done by Professor Ted Addison from MIT. I think he was also one of the speakers for the Shitsukan Symposium like 4 or 5 years ago, if I remember correctly. So actually the technology behind it is also photometric stereo. You can see there's actually several LEDs here when the surface presses the gel and it forms. And by illuminating it from different directions, actually very highly detailed 3D surfaces, like if there's, even if there are shape for the text on a $20 bill. So if we compare the geometric and photometric approaches, of course they have both advantages and disadvantages. As I mentioned, the geometric approach, because it has multi-view observations, so you can basically get a gross shape from 360 degrees. But sometimes the detailed shape is lacking because of the difficulty in the textureless area. And today's talk focuses on photometric approach. It cannot get the gross shape in general because usually the camera is fixed, so it only has 180 degrees. But it has very detailed shape information. To start this, there are some preparations or some preliminary about some concept. Here we represent the geometry using the surface normal. This is basically a vector. It's a vector that is perpendicular to the tangent plane to the surface. It only has 2 degrees of freedom because this is a unit vector, but it also can represent it using this 3D vector, like an x and y and n z. Another important assumption here is from our classic concept, we assume the surface follows the Lambertian reflectance assumption. So the amount of light, reflected light, is proportional to the dot product or the cosine theta between the lighting and the viewing directions. And here we assume the light is kind of the simplest model. It's a parallel or the distant lighting can also be represented as this kind of a direction. It's a unit vector in 3D domain. This can be achieved by using a point light source in a dark room like this one, but you put the point light source far away from your object. And given these representations, the Lambertian reflectance means that if the light hits the object, it uniformly reflected to all the directions, regardless of your viewpoint. When we have all these definitions, we can have the Lambertian image formation model. In a forward way, we will have that the observed scene radiance is proportional to the, this equation. So we have the intensity of the light, the albedo, this is actually the ratio of how much light gets reflected, times the dot product between the lighting and geometry. Now we can even assume that these scalars are equal to 1. Then we have, here you can observe that how the shadings and the image intensities vary under different lighting conditions. Now for each pixel, we can denote that its intensity under the first lighting is I1 equals to n dot L1. So in total, we have f different lightings. So we have n dot LF. And we can also expand them to the vector form. So we have this very simple equation. And we have millions of pixels, so we can either do the scan line or this way, horizontally or vertically. So finally, we can stack all the observations into a matrix. So here, each row is actually a stack of the vectors with all the under the first lighting for the intensity for all the pixels, so that we have this kind of very simple linear system that is I equals to n times L. And here we can assume that we can somehow use a mirror sphere to calibrate the lighting. So what we are interested in is in estimating the surface geometry. So we can solve this linear system by denoting n equals to I times the pseudo-inverse of L if we have more than 3 different lightings. And finally, the result can be represented using this figure. So here's the reference sphere. You can actually the RGB channels encode the NX, NY, and NZ, so that by checking the colors of the sphere, you can understand the green, the red, and the blue represent different directions. This seems to be a very interesting or a very simple problem, but we have very strong assumptions, and we assume that the surface follows the Lambertian reflectance. This is actually very ideal assumption, because in the real world, we have the general BRDF. We have some wonderful talks in the first two talks in this afternoon about the reflectance properties. And sometimes the lighting can be unknown, or it can be the general lighting. So in recent years, people are interested in generalizing the photometric stereo from all these aspects about the uncalibrated lighting, or we want to develop some robust approach by treating the specularity or the shadow as outliers, or we want to do the general material for the complex reflectances or the general lighting, or even using some data-driven approach to solving for the complicated case. In order to evaluate the photometric stereo under the general reflectances, we built a benchmark data set, which is called the Diligent. Here's the website to download the data set. And we are interested in still the very classical assumption, which is the directional lighting. So in our data set, we have 96 different lighting conditions. But we are more interested in the general reflectance or the complex reflectance, which is more realistic in the real-world objects. And more importantly, we want to provide the ground truth shape so that we can do the quantitative evaluation. In total, we have 10 different objects. Actually, from the left side to the right side, the difficulty of the problem is increasing. This is some very simple geometry, some generally diffuse objects, but here we have more broader specular and especially varying material. And along this direction, we even have some specular, highly specular, or the metallic paint, or even some mixed materials with this kind of convex shape. And below are the ground truth normals. So with this data set, we can evaluate the state-of-the-art or photometric stereo solutions for this kind of general reflectances. These are the methods that when we publish the data set, it's like in the year of 2016. And so we do the evaluation for the methods like that was like from the year of 2008 until the year of 2014. Basically, they have 2 approaches to solve for this problem. One is use the parametric model for modeling the complex reflectance. This is like in computer graphics, you have a lot of different models for realistic rendering. But here, we are more interested in, of course, we can use these models to write down an image formation model to have the general capability in describing how the light interacts with the material, but we are more interested in solving the inverse problem, meaning that the surface normal should be invertible. So here, still there are some methods that assume that there is a dominant Lambertian component, but there are some arrow or some outliers that can be represented using another matrix. Or you can use a different, this is actually our simplified Wald model, and you can use different weights by mixing Wald lobes with different weights to represent the surface object, the object surface. Or we can explore some general properties of the reflectance functions, like the isotropy, monotonicity, or some low frequency properties. So that because we are only interested in how to estimate the surface normal n here instead of the realistic rendering. And along this way, so these are all the non-learning or the data-driven approaches. Still, there are some progress that's made by, this is a joint work with Professor Imali Sato from NII, and we are proposing a new parametric model for photometric stereo that is specially designed for this purpose for the normal estimation. So these are some properties that we want to achieve when we're developing this model. So first, it should be very simple. It is a microfacet-based model, but we just have one a variable about the smoothness or about the glossiness. So based on the ellipsoid microfacet normal distribution function. So if you render it, it looks like this. And it should be able to be stable and accurate modeling property from very diffused to highly specular objects. By just changing the lambda here, we can cover this type of different material. This can be pretty much diffuse like the fabric, or this can be some metallic paint, but all these materials can be represented under this model. But for the inverse problem, like photometric stereo, and the most important property, it should be an invertible representation, just because it's only one parameter, and this is a forward image formation model. And actually, we developed our globally optimal solver that can be optimized in a very efficient way with global optima. So by inverting this equation, but because there are a lot of mathematical details, so I do not want to spend more time on this discussing this, but just to show the results on this diligent data. Here are too many numbers, but just to take a look at these numbers that are highlighted. There are 10 objects in the diligent data benchmark data set. Actually, this is our based on the Lambertian model plus some outlier, both of these two. And this is a method I just mentioned based on the mixture of the Wald lobes. You can see at that time, without the deep learning or data-driven approach, just with the parametric models, actually the average error for these are actually above 10 degrees in these years. But with this parametric model, the error is below 9 degrees. And here, this table actually contains two parts. The upper part is all from the non-learning based method, and the lower part is actually from learning based method that I will spend more time to introduce today. So these are actually comparable. Just to remember these numbers, you will see this table many times in the following part of my talk. You see this is like 8.9 something, but this is the 9 or some comparable numbers. Okay, now I will move to the more state-of-the-art solutions to this problem that is photometric stereo with deep learning. As I mentioned, so this is like a self-contained talk for introducing the recent progress. So these are basically like majority of the papers published in these years about this topic. And I just spent like 3 or 5 minutes on comparing them one by one. Not all of them are from our group. There are some papers from other groups as well. So in order to combine photometric stereo with deep learning, actually the first work is called Deep Photometric Stereo Network. They do it by using the fixed direction of light, meaning the training and testing, they have the same or the fixed set of lighting. And of course, this is not a practical setup. You definitely want to make it more flexible so it can support the arbitrary types of lighting directions as the input. So later in the year of ECCV 2008, yeah, coincidentally, these papers published at the same time, that they try to solve this problem either in a global manner or in a pixel-wisely manner. And in the year of CVPR 2009, there is an oral paper called Self-Calibrating Deep Photometric Stereo Network that to solve this problem in an uncalibrated setup. And yeah, after this, people will find that already for the diligent benchmark, that one has 96 lights. already seems there is some bottleneck. You cannot even improve the accuracy in a large step, but the problem is that we want to reduce the number of lights we have. So there are some recent works focusing on using the small number of lights for the complex reflectances by using the optimal directions or by using the kind of arbitrary directions. So there is also another work use unsupervised learning by using the reconstruction laws to solve this problem. And if you check the focus or some difficulties, these kind of challenges in photometric modeling, and these works, they have their own different focuses. Like for example, this one and this one, they propose some particularly solution to deal with the shadows. And these two papers, they are interested in modeling the BRDFs. And of course, there are more things to do about developing exploring more comprehensive feature representations. So let's start the first one. So this is supposed to be the first paper on using deep learning to photometric stereo. That one was published in the ICCV 17 workshop. So the motivation here is quite simple. So of course, we want to solve for the photometric stereo and a more complex and more realistic reflectances. And as I mentioned, there are some parametric models for the surface reflectance modeling, but these is only accurate for a limited class of material. And basically, like these benchmark data sets, they contain more complicated reflectances. And another thing is that the existing works, they mainly explore about the properties of the local illumination, and some global effect like the cast shadow is not well addressed in existing works. So the motivation of this work is that they want to just to model the mapping from the measurement to the surface normal using the deep neural network. So this is like a regression problem. And so because the DNN, it has a very strong capability, can express more flexible reflection phenomenon compared to the existing models designed based on some handcrafted or some physical phenomenon, a very simple network. So it's very straightforward. The input is just the images. Actually, one of the difficulties in designing a neural network to solve a photometric stereo problem is that you have a set of images. But this set of images, they are not like a video or in a temporal sequence, but they attach somehow with some lighting information. But for this work, the lighting is fixed. Meaning that for the training, for the testing, you use the same set of lighting, and the lighting is not part of the input to the network. So you just have L different images and or focus on a patch, and you put them like this way. And there are some dense layers to extract the features, to do the regression, and finally the output is just to the surface normal for this patch. But there is something interesting about the dropout property. At that time, we find that by considering this kind of problem, of course, this is usable if you want to make your training of your network to converge in a more efficient way. But we find that by randomly discard some of the images, or for one patch, discard some of the patches under some specific lighting conditions. So these actually are approximated simulation to the cast shadows, because if the light gets occluded, you will observe some dark pixels there. So this is somehow consistent with this kind of dropout property. Yeah, and by adding them together with the dropout, with the dense layers, and the loss function is also quite simple. Because it's the first paper, so this is just simply the difference, IMSE difference. And more, it's about the training. So we need to prepare the training data. And at that time, because we want to find some data that is realistic. So this is a real data, BRDF data that is quite popular in both the graphics and vision community. Although it has like captured 16 years ago, but it has a isotropic spheres of a real measured materials for 100 types of different materials, and we can use the blob, this kind of randomly generated shapes, with these measured BRDFs to render our images under different lighting conditions. And here again is this table, so we can see some numbers, interesting numbers here. So yeah, because this is kind of this baseline is the Lambertian photometric stereo, and these are the only learning-based method available at that time, and all these are the methods using either the parametric model or the general properties of the BRDS. You can see actually the improvement is just a little bit, because this one is actually comparable to this one if without the shadow layer, but seems that the dropout or the shadow layers is effective in like further reducing the errors for some specific objects. And so finally the average becomes a little bit lower than the existing method. It becomes below 10 degrees. Right, this is a performance of the firstly proposed deep learning approach. And particularly, it is kind of efficient in this object. This is this object. So this one is a very challenging object because it has this kind of concave shape here, which contains a lot of cast shadows. So with the proposed shadow layer, and the error of this object gets significantly reduced from 20-something until 16-something. So actually for that work, one of the most obvious disadvantages that it needs to fix the lightings for both the training and the testing. So starting from our year of 2018, and there are some more papers that are coming out to try to release this kind of constraint. The key idea here is this one is inverse rendering, and this is an unsupervised method. And of course, it needs to be it needs to use the reconstruction loss to get the consistency between the surface normal estimation and the appearance of the rendered objects. So it has a physically generative model. So here, the observation is X, and they want to disentangle the hidden variables like Y and Z. These can be the surface normal or the reflectance, the BRDF properties, but there are no GT, no ground truth of the shape, and no training data. So it works in this kind of iterative way by checking the appearance consistency by using the reconstruction loss, and of course the surface normal and the illumination as part of the input variables. So the network structure is like this. So it looks a little bit complicated, but just want to highlight some important factors. Of course, there is a photometric stereo network that try to get an estimation of the surface normal. And actually, in this work, they also use the initialization of the surface normal because you have a set of images and the different lightings, and the lighting information has been given. And even without using the deep learning, you can somehow run an existing photometric stereo method to get a rough estimation of the surface normal. But by using this one, you can calculate some, they call it the specular component. Because this is consistent with some observations in computer graphics as well. Usually if you check there is a very important vector, which is, sometimes we call it H. It's a bisector of the lighting and viewing directions. If you calculate that, the angle of that vector with your surface normal, you will probably have a large probability that you can get where the highly specular areas locate. So this is actually what they compute about the specular component. And this channel will be concatenated with the images together to guide the rendering process to maybe to highlight on where the reflectance, this kind of more complex reflectance should occur in this kind of a rendered equation. So this is to simulate the cast shadow. So you have the n dot L, and by including the cast shadow, and this is a reflectance map, which is the per pixel BRDF values, and this one will be multiplied with the shading term here in a pixel-wise manner, and this is actually the image reconstruction network. And if you check because there are no ground truths of the surface normal, so they need to apply an existing photometric stereo method like the baseline, the least square-based solution here. So the loss function is actually checking the consistency between the output of this photometric stereo network with the existing linear least square-based solution. And the other self-supervised loss is the consistency between the input image as well as the re-rendered image. And the result seems to, because this is like a second work, remember that number in the DPSN is about 9 something. And this one is able to reduce the error a little bit further, something approximately to 1 degree. So the average error is 8.83. But you will see that for like, this is how many, 8 out of the 10 objects, it achieved the best performance. And interestingly, in the year of ECCV 18, there are 2 papers that are focusing on this problem. That is to use deep learning to solve the photometric stereo problem for complex reflectances. And this work is called PSFCN. Actually, from the abbreviation of the title, you can get that FC actually means fully connected. This is an overview of the PSFCN. And actually, because these are kind of concurrent work, so this one is focusing on the same problem as the previous unsupervised one. That is to solve the dependency on the fixed lighting directions as the DPSN, which is the first work has done. So the goal is to given an arbitrary number of images and their associated lighting directions as input. So in this work, they put the lighting direction as part of the input. So you just attach another vector here. So PSFCN, this is still a kind of a regression work, try to estimate a normal map of the objects in a fast feedward path. And this is a network. You give the lighting condition because then this time you can change the lighting condition because it's kind of the input to the image as well. And finally, the output is still the surface normal. And the advantage of this work is it does not depend on a predefined set of lighting conditions, and it can handle the input images in an order agnostic manner. As I mentioned before, this is a set of images. It's an image sequence, but they do not have order because there is just a lighting information attached to each image. You can just swap their order. And this is how they deal with this work. So it has 3 components. Actually, you have different branches, which is equivalent to the number of how many lighting conditions you have. And for each one of the images with attached lighting, you go through another network in a concurrent manner. So they have a shared weight feature extractor just to extract some representations. And I think this is kind of the most important part of this work, that they have the Max-pooing layer, because you have a set of images, and they have been fed into this concurrent network of using many different branches. But somehow you need to unify them because you only have the only one set of the surface normal as our output. So we need this kind of fusion layer. And what approach they proposed here is actually the Max-pooing. And there is a normal regression network that tried after this kind of Max-pooing by fusing all the features from the different branches. They try to use this part of the network to get the surface normal estimation. So the loss function is also very simple. It's slightly modified. I think this is very easy to understand because actually for photometric stereo, what we are interested in kind of angular error, the numbers I have been shown many times, this is actually the distance between your estimated vector and the ground truth normal vector. So just to calculate the dot product or the cosine between them and use 1 to minus them. Here's a very quick slide about explanation about why they use the Max-pooing for multi-feature fusion. So this is an illustration of the difference between the Max-pooing and the average pooling. So the explanation is like, because the photometric stereo, the sequence, it does not have order. In order to achieve this kind of order agnostic operation, comparing with RNNs, this kind of a max operation has this kind of property. And also, so it can fuse an arbitrary number of features into a single feature. And also, it can track the most salient information from all the features. The training data is kind of similar to the DPSN. It also uses the blobby shape. And also the BRDF is 100 BRDF from the Merle dataset. But in order because this kind of shape is kind of smooth, and for photometric stereo, we are always interested in getting the very highly detailed geometric estimation. So they add these geometries with more details from another sculptured shape. And this is rendered with physically based ray tracer mitzvah. So this is also very useful in computer vision as well. So, and it's trained on synthetic data, but the evaluation is on the real data, which is again the diligent benchmark data set. Here you will see the arrow becomes 8.39. It's a little bit lower than the ICML 18 paper, and it achieves the best performance on these objects, especially these have more complex reflectances. But the performance on some very diffuse objects, maybe some of the conventional approaches without the data-driven can achieve even better results. And it is interesting to note that in that year ECCV, there is another paper from NNI from Professor Ihahara. This is a single author paper. It's also a solution for the same problem, but in a completely different angle of view. So what they are doing is that they propose a kind of new concept called observation map. This is a per pixel manner. And this is a kind of easy to learn representation. So here you see the equation is a bit complicated, but actually the intuition behind it is very intuitive. First, you need to normalize each image by its lighting intensity. So here we do not deal with the intensity, or this kind of irradiance changes caused by the lighting intensity. After the normalization, what you do is, this is just a quantization. You will have for 1 pixel, there is a surface normal, which is something you don't know, but you know the lighting directions. And the lighting directions, you can somehow project it onto this kind of image or this kind of a square grid domain by quantizing these kind of, by projecting the lighting Lx and Ly to the image, this kind of grid. So this each pixel is just an observation or the intensity values under a specific lighting condition. And by checking this is something very interesting is that for this kind of object with very strong cast shadow, you will see a lot of these observations. And there are also some strong values caused by interreflection. So by checking the distribution of this kind of intensity map, it also encodes some very useful information about the complex reflectance caused by either the general BRDS or this kind of global illumination. But the training data from this work is different from the previous works. This time they don't use the Mural BRDF, and they choose to use our cycles rendering in Blender and a set of 3D models and this kind of BSDF parameter maps from Disney's principled BSDF model, and generate the observation map pixel-wisely. And this is a quick review of Disney's principle, the BSDS model. And why they want to use this model, because the Mural is a real data set. Although it covers many objects with many different materials, from highly specular or wood or plastic, but you cannot guarantee that they are uniformly distributed or sampled. But by using this kind of parametric model, you can somehow do a more regular way of controlling how the material properties varies. So these parameters should be allowed to be combinations. There are more possible ways of combinations to make it as robust and plausible as possible. And the network structure is kind of simple because you have the per pixel, for each pixel you have the observation map. You can also do some data augmentation by rotating to different directions. And then each of them will go through CNN. And here is the structure is kind of dense net structure. And after that, because each of them will give a prediction of the surface normal at each pixel, and you can do the average of them to get your final prediction. I think I have a very detailed discussion with the author about this work, and the story behind it that because the network structure you see is very straightforward, and it told me that more important thing is actually how you represent the data. That's why they propose the observation map, which is an easy to learn structure, and also another thing is how to render more realistic data. Yeah, like maybe with Misabadu, we can do more realistic or complicated materials for photometric stereo as well. Again, this is result seems much smaller and becomes 7 degrees something. And here they have two types of result. One is k equals to 1. K equals to 1 means they only have one observation map for each pixel. K equals 10 means that they do some data augmentation by rotating to different angles and combine the or averaging all the predictions. And this is some another quantitative evaluation using their own, they call it cycle PS test data set, because this data set contains some objects, especially this kind of global illumination, which is not included in a real data set in our diligent. And in the year of CVPR 19, people begin to think about whether we can solve uncalibrated photometric stereo using deep learning, and this is an oral paper in that year. So the motivation is that for all these kind of existing works, this is kind of calibrating our results. And the PSFCN is from the same group, are in ECCV 18. And if you apply PSFCN, just without, remember that for the input of PSFCN, they need an image and attach this with the lighting condition. But if we just forget about the lighting condition, we can still get some results, but there are obvious artifacts compared to the ground truth. And this time they just want to solve the problem without knowing the lighting vector to hopefully make the result comparable to ground truth. So instead of a single stage method just to do the prediction, they want to do a two-stage method, but first do the lighting estimation and then do the normal estimation. Why are two-stage is better? Because the directional lighting, you have much fewer parameters if compared to the millions of pixels. This is easier to estimate. And then you can take the advantage of intermediate supervision. And more importantly, it will make this framework more flexible because you can just treat it as a lighting calibration method and follow the other state too, you can use whatever existing photometric stereo network. So the structure is pretty much to the PSFCN, are kind of from the same group. But what they need is not the lighting, it's actually the image and also a mask. And also they use the Max-pooing to fuse the features for the lighting calibration one. And then for the second stage, is it almost the same as PSFCN for the normal estimation. Well, something to say about the lighting estimation. So instead of doing the regression, it's actually a classification problem in this kind of discretized space, because this will have some tolerate to the errors. Because for this network, you cannot expect the output from the lightings here are very accurate. So they find that this kind of way gives better result. The normal is actually the same, so I skip this one. And again, the training data is the same. Let's see the result. So on the diligent benchmark, we comment in that paper that uncalibrated photometric stereo is kind of, there are a lot of open problems. So you see the results is much higher, the errors are much higher than the calibrated ones. But with this one, the SDPS net, the uncalibrated results are even comparable to the calibrated results before, and much lower error comparing to this non-learning based approach. Even for these very, very challenging materials in the USC light stage, without lighting calibration, it can give pretty much accurate result. So the last two works, I will just go through them very quickly. This is to try to reduce the number of lighting. Remember all the previous work I showed just now, they need 96, all the lightings from the diligent data set. So the problem is that can we still achieve the good result with just 10 different lightings? So this paper is in CVPR 19, and what they want to achieve is try to do the reduction. Because you have a dense, this is still based on the observation map, but you want to select the optimal set by reducing most of them. So they propose this kind of a connection table by solving an optimization, which is about actually they put it constraint the loss function to optimize this kind of sparsity. So finally they choose an optimal set of lights. And can achieve the 10-degree error with only 10 lights. And more recently, this is a paper that I co-authored. We want to do it in the opposite way, which is do the addition. We want to do the interpolation by giving a very sparse set of the observation map, still based on the observation map, but we want to use the generative network to get this kind of dense observation map, so that we can interpolate it similar to the image in painting. But what we want to consider is because it's a highly ill-posed problem, we need some constraints, like from the isotropic of the BRDF, or in this way, along this line. Or there are also some things that cause our observation map asymmetric, caused by interreflections and cast shadows, so there's another loss function to penalize this part. And the network contains lighting interpolation from the sparse one to the dense one, and normal estimation. This normal estimation network is almost the same as CNNPS in ECCB 2018. And finally, this is an interpolation result, and this is an estimation result on the, maybe we see this figure is more straightforward. The arrow is still about 10 degrees something, with only 10 lighting as input. So there are still some open problems for data-driven approaches, and these are some very classic data. This is diffuse. This is one of the famous CORS project in a computer vision course by University of Washington. And it's diffuse, it's 12 images, and this data was captured by myself 10 years ago. We find that the Lambertian photometric stereo works very well. But if you check the state-of-the-art deep learning-based approach, it seems they cannot adopt or generalize very well on this data. They have fewer lightings and pretty much Lambertian, and of course the image might not be that accurately captured as a diligent one, but seems there are still some space to improve for this kind of diffuse data with fewer numbers of inputs. And finally, we find that the diligent data set, it has a good choose for some kind of scan shape, but if the shape is very small, this is like 10 centimeter objects with a lot of delicate geometry details, we find that actually the scan is kind of blurred comparing to the photometric stereo. So this the scanning cannot be used as the ground truth for evaluating photometric stereo result. So I think the future, if you really want to achieve very high accuracy in geometric modeling, we need to somehow combining the scanning or this kind of geometric approach. This is based on structured light and also photometric stereo approach for very highly detailed 3D reconstruction. And many slides are adopted from my professor, my staff from Osaka University, and my collaborators from other universities. Thank you very much.
Thank you. So, any question? I have a question. So, in the former part, you proposed a new BRDF diffusion model, and I'd like to know why the diffusion model provides a better result. Is it precise to approximate the actual diffusion of object, or so is it possible to use for rendering also?
Yeah, this is a very good question. So actually this, because what we are interested in the inverse problem, surface normal estimation. So the proposed BRDF for this purpose needs to has two properties. First, it needs to be realistically rendered, like graphics models. And more importantly, it needs to be easily computed. Because if the model is very complex, it can render very realistically, but if the computation or the equation becomes highly nonlinear, then the optimization might have some problem. So we just take a good trade-off between these two. First, it can describe a broad categories of materials, and second, it can be easily achieved with a global optimization solver in a stable and accurate manner.
Okay, thank you. Any question? No? Okay. Thank you.
Yeah, thank you very much.
And so,